Hello and welcome you all to the 27th lecture of this NPTEL course, where we are discussing the standard model of particle physics, and we have basically defined and derived quantum electrodynamics for you, and we have also taken an example and we calculated the cross section using all the Feynman rules that we actually had for QED. And now today we are going to learn to compute the cross section in a different way, and that is called the Helicity amplitude technique. Okay, so let's get started and see what it leads to. So let's go back to the process which we actually discussed, like E plus E minus going to tau plus tau minus annihilation. Well, all right, you know, this is also something that we imposed, that the whenever the center of mass energy of the reaction is actually sufficiently large, then the masses of the particles involved, then it doesn't really matter that whether it is E plus E minus to mu plus mu minus or it is E plus E minus to tau plus tau minus. Although having said that, theoretical computations of cross sections are no different for those two cases, but how exactly you experimentally identify the muons or the tau, that's a different question, and I think that is something that you should ponder over. But for the time being, as I am trying to say, that the cross section calculation for E plus E minus to mu plus mu minus or tau plus tau minus, where you can neglect the masses, are equivalent. Okay. So, yeah, so we are here to kind of compute this cross section once more, but with a new technique which I call the Helicity amplitude technique. And this is a technique which is actually very useful because lot of devices, the softwares that you actually will be using to compute the cross sections in future, perhaps if you do simulations and all, these actually use the Helicity amplitude technique, not the trace technology which actually we used in the last lecture. Okay. So, before kind of getting into the mathematical details, first is to see what exactly is the Feynman graph. Let's draw it once more. So, let's remind ourselves that you know, we have an initial state electron and positron. So, the momentum for both the electron and the positron is flowing towards this vertex where this interaction takes place with the photon, right? And so, because this is an electron, so the spin flow or you know the fermion flow will be along the direction of the momenta, and for positron this will be actually opposite. So, the momentum that we assign is once again P1 for the electron and P2 for the positron. And what happens to the outgoing particles and antiparticles? So, we have a tau minus. So, both the particles come out of the vertex, right. So, the momentums are flowing out of the vertex. So, this is how we are drawing the momentum arrow, and then we have the fermion flow which will be along the direction of the momentum for tau minus and opposite for the tau plus, and the momentum assigned are P3 and P4, and of course, the mediator which takes a energy Q, and you all know that in this particular case it is a S channel diagram. So, the momentum which is carried by the photon is P1 plus P2, right. So, now with this let us try to write the matrix element or the amplitude of this process, and this is something that we can once again write remembering the Feynman rules that we actually derived before. So, first let us try to write the electron current, and so basically you have an initial state positron, and initial state positron will be defined by V bar of P2, V bar of P2 gamma mu, and initial state electron or annihilating electron, it is a particle, and that will be given by the spinor UP1, correct. And what about the tau current? The tau current will be, you have a final state particle which will be defined by, or a particle creation which will be defined by a spinor like U bar P3, and we will have a gamma mu coming from the QED vertex, and that is gamma mu here, and we have a final state antiparticle which will be defined by the spinor V P4, correct. So, this is how exactly the notation is. I mean, if you want, you can actually have these little subscripts like defining that these are the electron currents and this is for the tau or for the muon, okay, the u bar tau p3 gamma mu v tau p4. And then there is this prefactor of minus e square by q square. You tell me that this q square 1 by q square is coming from the photon propagator, which is g mu nu by q square plus I epsilon, and e square is coming from the proportionality of this electromagnetic vortex to the electromagnetic charge which is carried by this particle, and those are all proportional to the E, right. Now, once we write the matrix element in this particular way, the next thing to calculate the cross section is to calculate the matrix element squared. And in this process, you remember that we talked about this thing, that the unpolarized electron positron annihilation, that will basically require that you have to basically sum over all the helicity combinations that is possible in the final state, and you have to also take an average over the helicity combinations that are allowed, right. So, average over the initial state spin or the helicity and summed over all final state helicities is what is required in calculating the mod m bar square, right. So, this quantity that we see. So, in order to do that, what we do, that we take 1 by 4 and we write explicitly all the possible combinations which you actually have. So, we have mod of m r r square, mod of m r l square plus mod of m l r square plus mod of m l L square. This basically means that these are the combinations of the helicities of the initial state electron and positron. It can be right-handed, 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 left-handed, left-handed, right-handed, and left-handed, left-handed. But importantly, you have to also remind yourself that MRR square will actually encapsulate all the helicity combinations that can be produced in the final state. So, therefore, MRR square, this individual piece that we actually wrote over here, this will actually have the contribution coming from MRR to RR square, then you will have MRR to RL square, you have MRR to LR square and MRR to LL square, and so on. So on means that you can also write for MRL square, MLR square, MLL square, where all these combinations of the final state helicities will actually add up, right. Now, as I promised that today I am not going to use the trace technology that I did for the trace of gamma mu, gamma 5, etc., which we used in the last lecture to calculate the cross section, but today we are actually going to do the calculation using the helicity combination. So, the current that we actually have in the matrix element is actually of the form of psi 1 bar gamma mu psi 2. So, this is what is usually referred to as a vector current, right. So, QED actually provides you only the vector current interaction like psi bar gamma mu psi. I can denote it like psi bar gamma mu phi, say for example. But this phi, remember, is not a scalar, but this is also a Dirac spinor. Now, in the Dirac-Pauli representation, you remember that the gamma 0 was I 0 0 minus I, right, and you have gamma I, which is actually defined by beta alpha I, that is 0 sigma I minus sigma I 0. Now, gamma 0 gamma I therefore will be I 0 0 minus I into 0 sigma I minus sigma I 0. So, if you do this multiplication, which will give you 0 sigma I 0. Now, if I just want to write the component, you remember sigma 1 is 0 1 1 0, sigma 2 or sigma y is 0 minus I 0, and sigma 3 is 1 0 0 minus 1. So, these are the Pauli spin matrices, right. So, the gamma 0 gamma 1, this multiplication of the Dirac matrix will be basically 0 sigma 1 0 following this formula, and if you now explicitly use this sigma 1 like 0 1 1 0, it will take a form like 0 0 0 1 0 0 1 0 0 1 0 0 1 0 0 0. Gamma 0 gamma 2 will be 0 sigma 2 0. Now, what exactly this will be? If I use the form of sigma 2, this is going to be 0 0 0 minus I 0 0 I 0, then you have 0 minus I 0 0 I 0 0 0, right. So, this is what happens to gamma 0 gamma 2. What happens to gamma 0 gamma 3? This is 0 sigma 3 0, and this is actually 0 0 1 0 0 0 0 minus 1 0. So, you have 1 0 1 0 0 0, and this is 0 minus 1 0 0. So, this is basically gamma 0 gamma 3. Now, why did I write them explicitly? Just because I want to inflate this particular current which is actually appearing in the QED interaction, which is actually of the form of psi bar gamma mu phi, which from the definition that psi bar is what? Psi bar is psi daggered gamma 0, correct. So, from here I can say that psi bar gamma 0 phi will be psi dagger gamma 0 into phi. Now, what is gamma 0 gamma 0? Gamma 0 gamma 0 is actually gamma 0 square, which is actually equal to 1. So, then this will simply become psi dagger phi, and just if you assume that psi has 4 components, let us write them, that psi actually is assumed to have 4 components in the spinor. This is psi 1, psi 2, psi 3, psi 4, and phi also has 4 components, and these are phi 1, both are Dirac spinors, phi 1, phi 2, phi 3 and phi 4, correct. So, therefore, psi dagger phi will be simply the multiplication matrix multiplication, and that will give you psi 1 star phi 1, because psi dagger will be kya hoga? Psi dagger is essentially psi 1 star, psi 2 star, psi 3 star, psi 4 star, correct. All right. So, with this, then psi bar gamma 0 phi is essentially psi 1 star phi 1, psi 2 star phi 2, psi 3 star phi 3 plus psi 4 star phi 4. What happens to the first component? I mean, I am writing all the individual components of psi bar gamma mu phi. Now, you know that mu actually takes values from 0, 1, 2, 3, correct. So, I can ask this question, what are the individual components of this current that I want to actually find out. So, psi bar gamma 0 phi is simply this quantity, psi bar gamma 0 phi is just this quantity, and now I am calculating the next one, which is psi bar gamma 1 phi. Now, this is psi dagger gamma 0 gamma 1 phi. Now, gamma 0 gamma 1 is given by this 4 cross 4 matrix, which is 0 sigma 1 0. So, therefore, I have written the psi dagger here, and this is the gamma 0 gamma 1 matrix that we actually have here, and then we have the phi 1, phi 2, phi 3, phi 4. Now, if you multiply this one with this matrix, then it will turn out that this actually just gets reversed, like psi 1 star, psi 2 star, psi 3 star, psi 4 star just becomes psi 4 star, psi 3 star, psi 2 star and psi 1 star. This is a simple matrix multiplication. You can actually check that when you multiply this with this one as per the definition of matrix multiplication, you simply get this one. So, when you multiply, this is going to give me psi 4 star phi 1 plus psi 3 star phi 2, psi 2 star phi 3 and psi 1 star phi 4. Okay. So, this is the psi bar gamma 1 phi component. Similarly, I can calculate psi bar gamma 2 phi component, and that will be psi dagger gamma 0 gamma 2 phi, and once again you can use this gamma 0 gamma 2 and explicitly check. So, please check this too, which I am not doing here, but you can check it. Okay. simply matrix multiplication, you will see that the psi bar gamma 2 phi is turning out to be minus I into psi 1 star phi 4 minus psi 2 star phi 3 plus psi 3 star phi 2 minus psi 4 star phi 1. So, this is psi bar gamma 2 phi, and psi bar gamma 3 phi will be psi dagger gamma 0 gamma 3 phi, once again using this explicit matrix form of gamma 0 gamma 3, you can find out that this is turning out to be psi 1 star gamma 3 minus psi 2 star phi 4 plus psi 3 star phi 1 minus psi 4 star phi 2. Okay? So, you can check this. So, in this process we have actually calculated all the components of this current of psi bar gamma mu phi, where mu can take value 0, 1, 2, 3. Now, let us come back to the momentum configuration in the center of mass frame. Okay? So, once again this is a schematic of the collision, like E minus E plus producing a pair of tau plus and tau minus. So, momentum is P1, this momentum is P2, this is tau minus is producing a momentum coming out with a momentum P3, and tau plus is coming with a momentum P4. And you remember the definition of the center of mass frame, where we imagine that the collision happens in such a way that the P1 plus P2 is equal to 0, or rather P1 vector plus P2 vector is equal to 0. That means the three momenta of these particles are equal and opposite. So, that is basically the definition of the center of mass frame. So, in the center of mass frame, and particularly in the case where we are actually neglecting the individual masses and you assume this collision to happen along the z axis, so then you basically say that okay, for the electron I basically have the energy and I basically have the z component of the momenta, and just because it is in the massless limit, so those two has to be the same. So, P1 will be E 0 0 E. So, this is the energy and this is the Pz, and just from the energy momentum conservation, that this is E square equal to P square plus M square, which has to be which we are neglecting. So, we can say that the Pz is nothing but E. For P2, which is for the positron which is moving in the opposite direction in the center of mass frame, so we can easily write that the Pz component will be minus E. Now, what happens to P3? For P3, you see once again it is in the massless limit. So, therefore, the energy has to be E, and also we have to resort to the 4 momentum. So, P1 plus P2, the 4 vector, if you add, this is simply 2E. So, this has to be equal to P3 plus P4, correct? And in P3 plus P4, that you can always see that the whatever the x component and the z component of the momenta that you actually derive, those will also cancel. This is a result of being in the center of mass frame. So, you have nothing but to choose the energy of P3 and P4 both to be the E once again. Okay? So, P3 is E, Px is now E sin theta, just because it is coming out at an angle theta. So, Px is E sin theta, where Pz is actually E cos theta, and Py is equal to 0. And for P4, this is E, but the x component becomes minus E sin theta, right. So, this is minus E sin theta. So, you can imagine this to be the x axis, so to say, and y component is 0 and the z component is minus E cos theta, because tau is coming in this particular direction, where if you take the z component it will be minus E cos theta. So, this is essentially the 4 momentum assignment that we actually have for this particular reaction in the center of mass frame. Now, this is something that you can always do for whenever you are having a 2 to 2 collision in the center of mass frame, where you are neglecting the masses which I mentioned time and again, that me m tau or me m mu, so to say, is almost equal to 0 in the limit where the center of mass energy of this reaction square root of s is way larger than m tau and me. Now, we also remember that if we want to write the explicit binorial structures, those will actually have a factor of p by e plus m, right. So, if you remember how we actually found the helicity eigenstates of this u and v spinors, which are the solutions of the Dirac equation, those were having essentially something like cos theta by 2 sin theta by 2 e to the power I phi etc., with a factor of p by e plus m. Now, in the ultra relativistic limit, you can imagine that this p by e plus m will be essentially 1, right, because m is very small. So, e has to be equal to the p. So, therefore, we are in a position to kind of look into the possible helicity eigenstates with assuming that p by e plus m is roughly equal to 1 in the ultra relativistic limit. So, we had the definition of u up, which is equivalent of saying that this is my u r or right chiral particle, right helicity particle. So, the normalization factor is square root of e, never mind, square root of e plus m is usually the case, but once again we have neglected the mass, and this within the parenthesis is cos of theta by 2. So, this c represents cos of theta by 2 and the s represents sin theta by 2. So, this is cos of theta by 2 sin theta by 2 into e to the power I phi, cos theta by 2 is sin theta by 2 e to the power I phi for u up. Similarly, u down, which is representing the left chiral or left helicity state, which will have minus of sin theta by 2 cos theta by 2 e to the power I phi sin theta by 2 minus cos theta by 2 e to the power I phi. Similarly, you have the anti-particle spinors v up, which is the right handed one, which has the helicity eigenstate of plus half, eigenvalue of plus half, so to say, and this is actually square root of e s minus c e to the power I phi minus s c e to the power I phi, and v down, which is the left anti-particle, left-handed anti-particle, which is square root of e c s e to the power I phi c s e to the power I phi. Okay. So, these are the helicity eigenstates. So, what we are going to do, that we are going to use them in explicit, do this matrix multiplication to find the current, and then from there we would like to find the matrix element square for this particular process. I think this is understood, right? This is clear. Now, but before that we have to choose a possible electron configuration. So, say for example, a electron is actually coming with a theta equal to 0 and phi equal to 0. So, you remember that in spherical coordinates the theta is essentially defined with respect to the z axis, correct. So, whatever your vector subtends with respect to z axis, that is how you compute the theta. So, therefore, if this is the axis of the collision, is defining the beam axis, then theta is actually defined with respect to that z axis. So, therefore, you can say that the electron is exactly aligned in the z axis. So, the theta will be equal to 0 and the phi will also be, phi is the azimuthal angle, right. So, that is also going to be 0. So, if you evaluate this quantity from these expressions that we already have, what you are going to have, cos theta 0 is equal to 1, sin theta 0 is 0, cos theta is once again cos theta at theta equal to 0 is 1, and this is once again 0. What happens to u down? U down, if you look into, this is actually sin theta 0, this is cos theta, this is 1, e to the power I phi is once again 1, this is 0, and this is minus of cos 0, which is 1. So, this is what happens to so to say u up and u down in the experimental configuration in the center of mass frame, where electron is actually moving along the z axis. So, what is the possible E plus configuration? E plus configuration is moving opposite to the z axis, correct. So, therefore, theta will be pi and phi will also be equal to pi. So, in this limit, if you once again put it like E plus configuration, matlab the anti-particle spinors you have to talk about. So, the V up, once again from here you put theta equal to pi and you get V up is equal to square root of E 1 0 0 minus 1, and for V down, which is the left handed with a helicity of minus half, and that will be coming from this expression, and that will be square root of E 0 minus 1 0 minus 1. So, these are basically the helicity configurations of this particular reaction. Now, I also have to find the spinors for the final state tau configuration. Now, the tau is coming out at an angle theta with respect to z axis. So, you can say that this theta equal to theta and the phi is essentially equal to 0. So, with this your u up, the tau is a particle. So, you have to look for the particle spinors both right handed and left handed, but just putting theta equal to theta and phi equal to 0. So, you will find u up to be essentially square root of E C S C S. This is the right handed combination, and the left handed combination for the particle, which is u down or u left, so to say, is square root of E minus S C S C. So, this will be simply coming from these two spinors that we actually find out. And the final thing that we have to do is to find the tau plus configuration. But tau plus configuration क्या होगा? The tau is actually moving to the opposite direction. So, if tau minus is actually subtending an angle theta with respect to z axis, this will be essentially pi minus theta, correct? And also once again phi is going to be equal to pi. And so, we therefore have to evaluate sine of pi minus theta by 2, because all these angles are with respect to theta by 2, right. So, if you are making an angle pi minus theta, that means you have to evaluate sine of pi minus theta by 2, which is cos theta by 2, and cos of pi minus theta by 2, which will be equal to sine of theta by 2. Okay. So, with this the antiparticle spinors V up or V r is going to be square root of E C s minus C s, and V down or V left handed is going to be square root of E s minus C s minus C, right. So, this is basically the all the possible helicity helicities that we actually account for all these initial and final state particles that are there in this particular reaction. So, now what is left? We have to explicitly write down all these currents which we already have found out. So, we have the expressions for psi bar gamma 0 phi, we have psi bar gamma 1 phi, we have psi bar gamma 2 phi, and we have psi bar gamma 3 phi. So, we basically have to now do this matrix I mean the definitions are all there. We know what is psi 1 star, psi 2 star, psi 3 star or psi 4 star, and phi 1, phi 2, phi 3, phi 4 in terms of these spinors that we actually defined for the electron, positron, tau minus and tau plus. We just have to do this matrix multiplication to find them out. So, for example, what was the final state tau plus tau minus helicity configurations we want to first find out, and what was the current? The current was essentially u bar P3 gamma mu V P4. Let us actually confirm this once more. This is the tau current, right. So, this is the tau current that we have. So, this is u bar P3 gamma mu V P4. So, let us come back to this. So, let us try to find the RL configuration first, okay. The current for the RL configuration. RL configuration matlab when we say R and L, this nomenclature is like that we first identify the tau minus helicity and then the tau plus helicity, or mu minus helicity or mu plus helicity. So, basically by RL configuration I mean that the tau minus is essentially right handed. That means I should look for the spinor which is like u up P3, right, and L is tau plus. So, the tau plus is left handed in this particular case. That means we have to assign the V down P4 the spinor for this particular one. So, therefore, if I have to now find the J tau 0 for the RL configuration. So, all these calculations that I am doing is actually for the RL configuration, where u up P3 and V bar P4 is being actually taken into account. And once again J0 is therefore u bar up P3 gamma 0 V down P4, right. So, and following this identification, following this matrix multiplication that we have already done. So, this basically means that psi bar gamma 0 phi, this will be simply the multiplication without anything, because gamma 0 square is equal to 1. So, this is U1 up star V1 down, U2 up star V2 down, V3 up star V3 down, U4 up star V4 down, and we have identified all of this, right. We have that U bar up star, you know, so from here we have, and V bar V down is coming from this one. So, let us just multiply them and let us do this. Okay. So, U bar up star, so this will be actually, so this E becomes the common, right. So, square root of E becomes E, and this is actually the first term is CS. The second term is U2 star V2 down, U2 star is S and V2 down is minus C. So, this is minus C into S. Once again, the C means cos of theta by 2 and S means sin of theta by 2. All right. So, this is the second term. Third term U3 star V3, U3 star is C and this is S. So, this is once again plus CS, and U4 up star V4 down is S into minus C. So, this is once again minus CS. So, this combination is 0. So, the 0th component of the RL current of the tau plus tau minus is actually 0. So, now you can similarly calculate the J tau 1 component, which is U bar up P3 gamma 1. I do not want to mess it up with this one. So, this is gamma 1 and V down P4. So, if you multiply, this is to be E into minus C square plus S square minus C square plus S square, and that is nothing but minus 2E cos of theta. You can also calculate the J tau 2 component, that is actually U bar up P3 gamma 2 V down P4, which is going to be equal to 2IE, and the J3 tau that will be the third component is actually having the gamma 3 in between, and if you calculate, this is turning out to be 4E into sin theta by 2 cos theta by 2, which is 2E sin theta. So, now I am in a position to write the full 4 current, right, and so the 0th component, it is 0. The first component is minus of cos theta, you know, the J2 is I and the J3 is sin theta. So, this is essentially what I have for J tau RL configuration. Now, this is the exercise that I have to repeat for each of these cases, and I can find out that J tau RR is going to be, you know, U bar up gamma mu V up, right. So, this is the RR combination and it turns out to be identically 0. This is something that you should check. The other non-zero component is J tau LR, right. I mean, here we are saying that tau minus is left handed and tau plus is right handed, and in this particular case what you have to do, you have to evaluate U bar down gamma mu V up, and this is coming out to be 2E into 0 minus cos theta minus I sin theta. Very similar looking expression to that what we have for RL, and once again the LL combination of this tau state current is once again identically 0, where you have to find out U bar down gamma mu V down and just use this matrix multiplication, and it is going to be 0 0 0 and 0. So, this is the way that we could calculate the currents for the final state tau particles that are produced, and the same exercise I have to do for the electrons, and I am going to do in the next lecture. Thank you.